Welcome everybody. We're going to talk mostly about Python 2.5, but more generally how the Python standard evolves during the years with a focus on 2.5, but a little bit of historical introduction as well. After the brief introduction about what happened between 2.2 to 3.2.4, we're going to move mostly to 2.5 and basically what's really hot about it, the with statement and the whole concept of resource acquisition is initialization, other language changes and standard library and optimizations. And then Q&A, but Q&A is also welcome during the talk as usual. So what's Python? Python is one language with many versions. You've heard of Jython. It's still pending, a bit late, but eventually we'll get there. A 2.2 to 3 release. You probably heard about IronPython, who's apparently quite the success at Microsoft. IronPython 1.0 was released in August at Microsoft, and it's basically the equivalent of the classic Python 2.4. You may have heard of PyPy, the research project of the European community, which is, again, basically equivalent to Python 2.4, but not quite ready for production yet. And of course, what we normally refer to as Python is a reference implementation known as CPython for either classic Python or Python implemented in C, take your pick. 2.2 was released just barely within 2001, and then there were follow-up releases until 2003. Meanwhile, right after that, 2.3 was released in the summer of 2003, with follow-on releases all the way to 2005 and so on. What was in 2.2 was a lot of major new stuff. It was really a major revolution in the language. What was in 2.3 was mostly optimization. 2.4 had some optimization. We'll see the balance about that. 2.5 has substantial optimization, probably higher than 2.4 over 2.3, but it's also got substantial new features. A more graphical presentation of the same concepts is in this timeline, where you see where 2 through 2.3, 2.4, 2.5 fit, and where all the minor language releases come. 2.2 was really a revolution, a backwards compatible revolution. Basically, just about everything you had for 2.1 kept working, but a lot of new stuff was introduced that really made your life much better as a Python programmer. The new style object model, the descriptors to make it work, the ability to have custom meta classes pretty easily, iterators and generators, a completely new model, nested scope, lexical scope, which didn't used to be supported, the start of the long process, which is not quite completed yet, merging int and long, the new concept of division, which again isn't quite completed, the new bool type was actually introduced in a sub-release to 2.3, and a lot of stuff in the standard library, XML, RPC client and servers, support for IPv6, the new email package, the possibility to compile with Unicode encoded as UCS4, which I'm told is quite important in some Asian locales. There's never been anything that big since Python 2.2. We also got a new rule in the following up releases of Python. We will never anymore introduce new stuff in 2.n something that wasn't in 2.n. We did in 2.2. Bool was introduced smack in the middle of the life of the release, and that made for no end of trouble. But we'll never do that again anymore, promise. So the main things, having to summarize out of the lot of stuff that was in 2.2, was the ability to make new classes, new style classes, generally by inheriting from object, but you could also explicitly set the meta class instead. Meta class equal type is the same thing as inheriting all otherwise ancestor-less classes from object. The ability to easily make and return lexical closures, as in the FunMaker example here. Generators with the new yield keyword, which of course being very new had to be explicitly enabled with a from future import at the time. And more generally, the iterator model, including the 2-argument iterator using a function and a sentinel. I'm not going to go over any of these in any detail. I kind of assume you guys are familiar with Python 2.2 or later, so all of this shouldn't be new to you. But these are all huge things introduced in Python 2.2. In comparison, 2.3 was a very stable evolutionary step. Essentially, there were no changes to the language proper, same syntax, same semantics, some minor tweaks in corners of the languages most people never explore, such as the method resolution order for multiple inheritance was substantially enhanced, but so that may count as a change in language semantics, but most people wouldn't notice. On the other hand, there were a lot of optimization tweaks and bug fixes. Among the most significant one, we gained the ability to import from zip files. Sort, which used to be one of the fastest in the business, became incredibly faster than it used to be. Multiplication of long finally adopted a modern advanced algorithm, Karatsuba in particular. Memory allocation in the Python internals was consolidated into the new PyMalloc concept. And minor stuff such as interned string can be garbage collected and so on. A lot of new built-ins, which I'm not counting as part of the language proper because they're technically in the built-in module, such as sum, enumerate, the ability to do extended slices on everything. The extended slice syntax was already there, but basically wasn't supported by all the built-ins before 2.3. And many enhancements to all built-in types, str, dict, list, file, and so on. And many new modules in the standard library, BZ2 for better compression, CSV for comma-separated variable files, the datetime module for very handy unified handling of dates and times, heap queue for heap processed priority queues, iter tools to make using iterators even easier, logging, a huge framework for logging, opt parse, a replacement for the good old get opt, the platform module to get all sort of information about the platform you're running on, the sets module to give you the new data type sets and in variable set, frozen set, tar file to handle guess what kind of files, text wrap to do text wrapping, time it for easy, reliable micro measurement of performance, and a lot of enhancement in existing module. For example, 2.3 is the release where sockets gained integrated the timeout functionality, which used to be a third-party module you had to download separately and integrate with your Python installation and work with. Now, since 2.3 Python socket, you can set a timeout on, so they will time out when you want, as opposed to when the TCP IP kernel in your stack wants, which is generally pretty hard to control. So 2.3 didn't really change the language, but it changes a lot else. That's sort of par for the course, our creativity being constrained because we decided the language needed stabilization. A lot of it went into the standard library. Nevertheless, these are some highlights, basically from library changes. You can have a zip file instead of a directory on the sys path and import from there. You can do the sum of a series of numbers very easily. You can get the index as well as the content with the new enumerate built in. You can print the reversed version of a string by indexing it with extended slice syntax with a negative stride in this case. We had universal new lines to support files maybe mounted on some file share on your LAN that may be using standard Unix line ending or Microsoft style line endings or even others, and many other new modules. So moving on, we then got 2.4. Mostly evolution, not quite as purely evolutionary as 2.3, but mostly. What we added to the language was basically generator expressions and decorators. And a lot of teeny optimization. Most of the low-hanging fruit are already been picked in 2.3, so the average program in 2.4 may gain 5 or 10% performance, but it's still worth having. That 5 or 10% performance comes from like over 100 fixes specifically aimed to performance. New built-ins, sorted and reversed, basically mimicking the existing method of list, which however work in place, and therefore require you to copy your sequence into a list and then do the call to sort or reverse and then use the new thing, sorted and reversed, to work on the fly, much more practical for many cases. Further enhancement to sort, such as the ability to pick the sort field with a key function, key equals argument, many enhancement to strings, sets, having proved their usefulness in the standard library, became built-in as being a very fundamental type, so there's no need anymore to pervert the use of dictionaries to actually represent sets. Standard library gained many new modules, collections intended eventually to hold those sort of container types. It started with a double-ended queue, cookie lib to centralize and facilitate client-side handling of HTTP cookies for session processing, decimal, a crucial enhancement fully compatible with the decimal floating point standards to let you do, when you don't really care for speed but want reproducible decimal results, instead of the whatever kind of binary floating points your hardware supplies, with decimal you can get repeatable, totally portable decimal floating point results. And sub-process finally unifying and putting at a high abstraction level all the sort of function you used to do with OSDOT system, OSDOT pipe, the pipe2 module, and so on and so forth. And a lot of additions and enhancements to existing modules, such as the new submodel string.template, much faster implementations of the bisect and heap queue modules, a couple of new stuff in operator module to facilitate the key equals usage, item getter and utter getter, urandom to get actually physically random bits, or at least cryptographic quality random bits if your platform supports them at all, local storage for threads. I could go on for hours, but I'm not going to. I'm just going to summarize a few language changes. So the first example shows you doing the sum that I'd shown for 2.3 without actually instantiating the list as such. You don't care to take up a megabyte to store the list. You only need one item at a time, and the generator expression syntax lets you generate the list one item at a time rather than in memory all at once. And the @class method notation in the second snippet shows a teeny syntax difference. Is basically identical to what you used to have to express as bar equal class method of bar right after the def, but it's substantially more readable, and it caused an explosion of the use of this kind of higher order functions in Python in the wild. And then some new built-ins, such as sorted, which is typically used, for example, in a for loop without altering the sequence you pass to it, reversed, same difference. By the way, this is identical to the existing extended indexing, which I showed earlier with a -1 stride, but it's much more readable. And set and frozen set as built-ins. Some built-in additions, such as, for example, I cherry-picked a few, the new center method. The center method was already there, but you can now pass explicitly what filler is to be used for centering the string, such as you want the field centered in the string centered in a field of 7, length 7, with pluses around it instead of spaces. R splits from the right, just as splits from the left. This is an example of sorted with an explicit key function. This shortest first and doesn't alter the order. The sort is now guaranteed forevermore to be a stable sort. So the order of items of the same length, such as D and G in this example, is guaranteed not to be altered. Since they have the same key, they maintain their existing order. They never get compared. And I did mention the new standard library modules, such as the dequeue type, which lets you append and extend to the right and the left, the decimal module, the IEEE 754 implementation, the sub-process module to spawn and control sub-processes, and the various additions to the standard library, such as item getter, urandom, the local, which I already mentioned, a couple of new functions in heap queue to get the largest n and smallest n items. Sometimes I get asked, why don't I just sort and slice? Well, sorting is n log n. Suppose you want the biggest 100 item out of 1,000,000. If you sort the 1,000,000 items and then slice, you're paying a price proportional to 1,000,000 times the logarithm of 1,000,000, which can become pretty costly. If you just call heap and largest, you pay a price which grows with the number of items you want, or the greater of the number of items you want and the number of items you've given it. It's basically a linear algorithm using a priority queue. So that concludes the rapid historical excursion, and I'm now ready to move on to 2 to 5. That it might be a great moment if anybody has questions or doubts about 2 to 3 to 4. Otherwise, I'm just going to proceed to 5. Okay. So, in 2.2, we had a revolution. 2.3 was very evolutionary. 2.4, almost evolutionary. 2.5 keeps stretching the concept of evolution of a stable language. I would say evolution plus, because there are actually several language changes. One of them is huge. We now have full support for resource acquisition as initialization style programming. Anybody who comes from, say, Java will think it's no big deal. Anybody who comes from C++ should recognize how big it is. We'll delve into that. We have stuff to support it, such as generator enhancements and a new module called contextlib, which exists specifically to support the new with statement, which, by the way, has nothing to do with the with statement you may know from Pascal. It's a completely different concept, more similar to the C# using, if you're familiar with that. And then plenty of little things, such as new kind of imports, a new kind of try statement, new operator, ternary operator, and a pretty big revolution in the exception subsystems. A few new built-ins, any and all, and a missing method, special method of dicts, and several new standard library modules, of course. Any Python release has got to have at least 5 world-changing new library modules apparently. But nevertheless, there are many optimizations. There was actually a whole sprint in Reykjavik, Iceland, sponsored by EWT, focused exclusively on performance optimization. I think the name was Need for Speed. I wasn't there, but I think Neil was. Oh, okay. Nobody was sitting here was actually able to make it. Nevertheless, they made a lot of huge optimizations. Sets and frozen sets were recorded from scratch. Instead of basically sharing the mechanics of dictionaries, they're now strictly optimized for use as sets and dict sets. String operations got many speed ups. Some of them are unboundedly huge. For example, search of a smaller string within a larger string with an in operator used to use the trivial, obvious algorithm. Well, check the first character until you find it, then step on the smaller string looking for the second, third, and fourth. The trivial algorithm you could basically code without thinking. It's order m of n, m times n, where m and n are the length of the two strings. Now in 2.5, we've got a subtle specialization of Boyer-Moore, which basically is of a better big O behavior. It's big O of m plus n, essentially. So there is no limit to how much time you can save with that. If you were looking for a 1,000,000-character string within a 1,000,000,000-character strings, your programs are easily going to be thousands of times faster. Now, you shouldn't do that, probably, but if you did, you're going to be amazed at how much your very slow, used to be very slow program has become extremely fast. Structures speeded up, new style exceptions are much faster. That not very significant. You're not supposed to raise exception as all that often. The main reason to make exception new style wasn't actually to speed them up. It was basically to get all the advantages of new style classes, but a nice side effect is that it's now much faster to raise an exception. And many minor stuff. Most optimization work is teeny thing that give you 2, 3, 4% here and there and there and here and there. That's how you eventually build up to a big speed up, except where you have some big stuff, such as optimizing string search from trivial algorithm to Boyer-Moore and so on. Regular expression module now uses the Python allocator. Function calling has been made faster by simply keeping one unused frame around if available at any time. It's like the typical free list thing, but just once. We didn't go crazy like sometimes people do with per type specific free lists. And the new compiler can actually do a little bit of cost unfolding. So if you write sex per day equal 24 times 60 times 60, it is not computed at runtime but at compile time. Not a big deal, but it encourages you to use this rather clear way of expression. An optimization that can be huge in some cases is when you're importing something, the importing subsystem now caches the results of whether this file or that file exists or not. Instead of repeating questions to the operating system, stat system calls. I need to import foo. Does blah, 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 slash foo py exist? No. Does blah, 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 slash foo py exist? No. It remembers the answers that the operating system has given. This is a minor win if you're importing from a local file system. If you're importing from NFS or SMB or other network shared file system, it can make the startup of your program orders of magnitude faster. We can see that as a big performance improvement, or we can admit that the architecture of the previous system was totally broken with compared to network shared file systems, or we can turn the thing around in saying that the network shared file systems are totally broken because they try to be transparent, try to emulate local file system, but never do a good job. But that is worth a 1-hour talk in itself, so let's skip it. And let's move to the meat, the big, substantial, enormous improvement of Python 2.5. Resource allocation is initialization. Something that happened all the time in 2.4 and all earlier version of Python, and happens all the time in Java, is something like resource equal some expression that allocates and return a resource. Try a block of code using the resource. Finally, a block of code freeing the resource. If you use this resource in a 40 different pieces of code in different modules, this goddamn boilerplate is going to repeat again and again and again. You hope. Because if it doesn't repeat, you have a bug. Somebody forgot, whoops, to do the try finally. So they just use the resource and then free it. And then if in the use there is an exception, the resource is never freed. And you accumulate open file handles, or maybe never free a lock and end up in a deadlock, a nightmare. Which C++ programmer, looking down their noses at us, said, well, we don't have that problem. We use constructors and destructors because we have on stack auto allocation, which guarantees freeing at exit of block. Finally, we can give a substantial retort to that feeling of superiority. The with statement saves us, or at least our pride. With block expression allocating as resource, use the resource. The freeing is automatic. On exit of the block, whether it's a normal exit or an exception exit, you get out, and their source gets freed. So what does it need to use this? Well, many existing types have been made ready to support it directly. For example, files. Typical example, you want to make sure a file is closed as soon as you're done with it. How do you do that? With open the file path as F. The file type returned by the open function is now perfectly adapted, as we'll see what that means in a short while, to be used inside the with. So the close method is automatically called as soon as you exit the block. Same for locks, another great example of resource acquisition as initialization. Say that somewhere in your code you have one global lock called sumlock, an instance of threading.lock. Now, instead of having to do sumlock.acquire, try blah, 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 finally sumlock.release, and if you forget, you keep holding the lock in case of exceptions and so on. Now you just do with sumlock, all the code you want to execute as a critical section, protected by that lock. The with itself makes sure, we'll see how, that the acquire method gets called on entry, and the finalization of the resource is the release method. At block exit, no matter whether it's a normal exit or an exceptional one, you release it. So to actually enable the with statement, you have to import it from the future. Every time a new keyword is introduced, it always has to wait one full release to be a full citizen of the language. So that if you have any code that actually uses with as an identifier, it could happen, it's not going to be broken. You will be able to run it just fine in Python 2.5. To make with into a keyword, you have to in 2.5, you have to explicitly import it from the future. This gives you about 1.5 years or whatever it takes between two releases to fix all your old code, removing all your instances of with used as a plain identifier, name of a variable, a function, or something. In 2.6, no doubt, it will be automatic. So after you've done that, in modules for which at the start of the module you have this import from the future, you can use with expression optionally as var. You don't have to actually have the as var clause if you don't care about the value like we saw with the lock. Then any block, typically an indented block. What does this mean inside? What does it do in terms of Python internals, so to speak? It's essentially the equivalent of what follows. The expression is evaluated and assigned to an anonymous variable, which we will name underlying context just to be able to tell what we're speaking with. Then the enter method is called without arguments on that context object, context manager specifically. But the result of that is assigned to var if there is a var, an as var clause. And then the with block is executed in what amounts to the same thing as the try close of a try except else statement. Note I'm using a try except else and not a try finally. Why? Well, because it makes a difference whether the with block terminates normally or not, because a special method called exit gets called on the context manager, but it gets called differently depending on whether the termination was normal or exceptional. For a normal termination, the else case here, it's called with 3 arguments, none, none, none. This means everything went just fine. If there is an exception, then the exception type, value, and traceback are passed as 3 arguments, which are the same things returned by sys.xinfo. Is there an explicit?
Is there an implicit raise? In other words, does that actually catch these?
It's subtler than that. I wanted to make it a three-liner. It depends on what context set it returns. It can return none, or it can, or a false value or a true value. You can look at the PEP if you want these very, very fine-grained details. I don't think you should write your own context object, as I'll explain later, so I'm not getting into this level, but good catch. Yeah, the pseudocode as written, I believe, by Guido in the PEP wouldn't fit on the slide because it catches everything very punctiliously. This is just a hand-waving proof of concept level. So, anyway, my point is that we can now retort our C++ brethren for their year-long feeling of superiority. We're better now. Actually, Matt Ostern, the main shepherd of the next C++ standard works here at Google, we happened to start at the same time, so we got friends by taking the introductory courses at Google together. And I also admire his book very greatly, Generic Programming and the STL. If you want to start understanding what generic programming is, that's probably still the best one. Anyway, he happened to sit into my presentation. He's not a Python programmer, but he was looking at this and saying, we got to have some of that in C++. I don't know whether anything will happen, but because, yes, sometimes the fact that a destructor cannot know whether it's being called because of a normal exit or an exception means trouble, so you do all sort of tricks to actually distinguish, and we don't have to. We're better for the moment until possibly the next release of the standard. So you can write your own context managers. You can write them just as you can, say, write your own iterators. You normally shouldn't, because generators are so much handier, but the whole protocol is exposed. You want to go ahead and write your own iterator, go ahead. Similarly, you want to write your own context manager, write a class. It will have some init, because you probably want to initialize it. It will have an enter and an exit method. Make sure enter returns some useful variable, and exit performs whatever is needed for termination. If you need to distinguish whether the termination is normal or not, check if all arguments are none. Actually, I think you can just check the extension type. If the extension type is none, then it was a normal terminator. This is extremely general. You can do absolutely anything you want. However, if you actually had to do it all the time, it would be sort of chunky. Like for iterators, you can do it, but after you've written 6 or 12, it starts getting old. So what do we have that's better? I don't know, but let's give an example. Very simple one. Let's say we want a transaction on a database. We're using the standard Python API for database interfacing, the DB API. So we get initialized with some connection object. We wrap that, basically record what we're being initialized with. At enter, we generate and return a cursor on that connection. So the caller does the with transaction blah blah as cursor and does all the cursor execute, cursor fetch, blah blah. If we exit normally, we want to commit whatever that transaction did to the database. If we exit abnormally, we want to roll back automatically, and that's trivial, because we just check the exception type. If it's none, we commit, otherwise we roll back. And yes, this implicitly erases the function, which I didn't get into. So the use is trivial. With transaction on the connection as a cursor, cursor execute this, blah, blah, blah. All the complication of remembering and finding out whether you want a commit or a rollback is encapsulated once and for all by that class. But you don't necessarily have to write classes like this one, because you get the new context lib module, which helps a lot. Essentially, the main thing is contextlib.contextManager. It's a decorator. So you prefix it to a function, but specifically, It's intended to decorate a generator. So you write your context manager as a generator. Basically, instead of inventing new syntax, we repurposed, if you will, the existing syntax and semantics of generator, not for looping purposes, but specifically for the purpose of doing context management for our AII. So your generator should yield whatever you want the result of enter to be. Under. You normally, actually, invariably, do it within a try finally or a try except else. So the yield is in that try clause. Because in the try except case, in the case an exception was raised, you normally raise it again. In this case, there is nothing implicit. You want to re-raise it again. But remember, the raise statement without arguments just raises the current exception, so that's not a problem. You have a few other things in context lib. Oops, sorry. You have a few other things such as nested, which basically you call with several context manager applies them nestedly, so you don't have to actually nest to the with statements. Be nice. And closing, for the very special case where all you need to do is to yield the subject and call close on it when it's done, closing does that for you. These are rather special cases. So how do you implement a transaction with a context lib? It's not all that much shorter than writing your class, but it's like more organized. So basically you have a function, which is actually a generator, which does its initialization, which is very simple, of course, and then in the try clause of a try except else, does the yield of what you want the result to be. And in the case of the exception, you do the exception processing, the rollback here, and re-raise whatever exception it was. The else is the branch you get into when there's no exception, and then you do the commit. And that's it. And the decorator context lib context manager wraps that into a full-fledged context manager. And you say the underscore key of your keyboard. That's the main advantage, because you don't have to type under, init, under, enter, under, exit, under. With the price of an upper-end laptop and the cost it would be to replace the underscore key, the saving in dollar amounts a lot. But okay, this is the example of the use of nested. Say you want a locked transaction. Well, you could do with the lock, colon, indent. With transaction, blah, blah, colon, indent. But one of the principles of the Zen of Python, flat is better than nested. You want the nested semantics, but you'd rather not keep indenting your stuff. Well, you call context nested with all the arguments you want to be context managers nested into each other, and you get whatever the result as a tuple of results. And so your body here is just once removed. I believe it's first in, first out. No, first in, last out. So it does the locking, then starts the transaction, then ends the transaction, and then releases the lock. Yeah, that's it. And in the simple cases where all you need is to make sure a .close method is called, that's what closing is for. For example, I said that built-in files do that automatically, but say, for example, the pseudo files you get from urlib.urlopen don't, but you still get them to do it by call it with context lib closing, instead of just saying f equal or with urlib.urlopen, which wouldn't work because that's not a context manager. You make it into a suitable context manager with a trivial enter and an exit that just does the close. Just because there's so many things at once that are almost like files but don't support this newest. You may have noticed, if you're really a Python expert, that what I suggest here, you couldn't write that in Python 2.4. It screamed bloody murder at you. Did anybody notice that? Have you ever wanted to put a yield inside a try? I have. But you couldn't do it. Now, you can. And that's one of the great benefits of AII. We had to support that to let context slip work. So it now works in the general case. Yield can be now inside a tried clause. So how do we guarantee that it finally happens in a general? I mean, if you're expert with Python enough to understand why it didn't work, you may remember the objection. So why did they go away? How can we make it work now? We can, because yield is now an expression. It's not a statement anymore. Remember, any Python expression can be used as a statement, but not vice versa. So yield is now an expression. You can keep using it as it was, because it's still valid as a statement, but it also has a return value. So what's that return value? Well, if you have Python 2.4 code and just move it to 2.5, the return code will always be none. But there's a new method in generators, which is send. Instead of doing g.next, which is all you could do on a generator, implicitly in a loop or explicitly in your code, you can, if you wish, call g.send passing a value. That value becomes the result of the yield. Those of you who are CS majors may be starting to recognize code routines here. It's not a full-fledged code routine, but pretty close. gnext still works, but it's like said, it's become a synonym for gsend none. So basically, gsend is a new gnext, except it also takes an argument, an optional argument, if you will, because you can still call gnext, and in those cases it defaults to none. A widespread opinion, I don't know if Guido shares it, is that a yield result that actually returns a value should always be in parentheses. It makes things so much clearer. Otherwise, it's sort of And a new method, the throw method. You have a generator object, you can now call g.throw type value traceback. So you're raising the exception with a certain given type and value and traceback inside your generator at the point of the yield. And a new method, g.close, which is a shortcut for g.throw generator exit, where generator exit is a new kind of exception, of course, which just means, okay, I'm done with you, terminate this loop. Finally, when g is garbage collected, g.close gets called on it if it already hadn't. Woof! So finally, we can use try finally or try except or try anything within the generator. Yay. So besides, this has a lot of other advantages. For example, it's pretty normal to start looping on a generator but end prematurely. We'll like that as soon as we've found like an item in the generator that satisfies the condition, we break out of the loop. So what? So what then? Does the generator stay around forever? Or until it happens to be garbage collected, or what? Well, now we know. We want to make sure the generator gets closed. We can explicitly call its close method right then and there. And remember, we can also have a with statement with context lib closing to make sure the close method is called on any object as soon as possible, as soon as we exit the loop. So that's one possibility. Otherwise, the semantics of what gets finalized when is very sharp now. So this is, to my mind, right after the optimization is 80% of the motivation for wanting to use Python 2.5. The with statement, the generator enhancement, and the context lib module that tie them together. But there's plenty more. But wait, there's more. For example, I'm sure you're familiar with the problem that imports in Python are, by default, and you can't really change it in any way, relative. So if you're working inside a package, and that package has a module called foo, there is it's hell from inside any other, or including itself, any module in that package to get at a global module foo, a module foo that is on some directory on syspath. Because in port foo, the relative interpretation takes precedence. That's sort of like the typical beginner mistake in Unix. So I've written this program called test, but it doesn't work. Well, no, because the built-in called test takes precedence, so you have the problem the other way around. So we finally took the first steps toward fixing this stuff. You still have to import that from the future because by default, anything that works into 4 will keep working into 5. We do not break good existing code. That's our mantra. But if you do import absolute import, then the meaning of import changes. Instead of looking first in the local package, and then if it can't find it there, go into syspath, it goes to syspath only. Forget the local package, that has nothing to do with the case. If you want to go to the local package, you use the new syntax, .x. And if you actually, this has been slightly generalized, and some might say overgeneralized, you can go to the father package of the current package with the syntax .x. I foresee the potential for a overuse of this powerful feature, but there are real use cases where you really want to go to the parent package, so basically this supports any number of dots. If you exceed about 200 dots, you are in serious trouble, psychological trouble. Not, but anyway. So right now, since you need to import from the future, most people will completely ignore it. But it does promise an important simplification of import semantics in the near future, a couple of years from now when 2.6 comes out. I hope in 2.6, the relative absolute syntax and semantics will become the default. Something that our Java brethren used to hold against us. In Python, you could have either a try except or a try finally, not both. Basically, you had to nest one inside the other. While our Java friends, Java using friends, were using except and finally in the same statement and surviving just fine. So we finally can do that in Python too. The semantics is pretty obviously that the finally gets executed last. So it's equivalent to this kind of nesting, and you can still write. And you can also have an else clause, which we still have, and Java doesn't. And that's the else of the except, because it wouldn't make any sense to have an else for a finally. Finally is always executes unconditionally. The else is a clause that executes if no exception gets raised. Okay? Possibly the most controversial feature. I think it is there, but he's carefully making believe he's not listening. Possibly the most controversial feature of Python 2.5 is that we have unfortunately gained another thing our C++ brethren vaunted longly, the ternary operator. We do it with the condition in the middle and the values left and right. And technically, you don't even have to use parentheses, which I'm sure will have huge. Let's move on to something a bit less controversial. Exceptions are now new style classes, and their hierarchy has subtly changed. I don't know how familiar you are with the exception hierarchy in 2.4 and earlier, but basically, you couldn't really do an except exception without involuntarily catching the poor guy who was banging on Control-C because he really wanted, the poor developer generally, really wanted to kill your program, Control-C, 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 but you were catching all exceptions, and that unfortunately included his keyboard interrupts. So now, keyword interrupt is not an exception. We have the new class base exception, which is a new stop class. And then there's exception and all stuff under it, but system exit, this explicit call of system exit, and keyword interrupt do not derive from it. So if you do an except exception, yes?
System exit appears twice in that way. Oh. Yeah.
Where?
System exit appears twice.
I see generator exit. Oh, whoops. Okay. So it shouldn't be here. Thank you. Yeah. Well, it's a very important exception, so we decided to place it as two. Okay. All right. It's a mistake of mine. Whoops. Yeah, the point was actually accepting system exit and keyword interrupt. I think memory error should also have come out, because if you're out of memory, you're in real trouble. But there was a lot of debate on that, and this was the compromise. There's a couple of new built-in, extremely simple ones, but then so were many ones that were introduced years ago, like some, and yet they made a difference, because it's psychologically very different to have it there. It's any and all. Pass it as sequence, they loop, and exit as soon as, they short circuit, they exit as soon as they know the result. By sequence, I mean any iterable, of course. Note, one big thing, was some debate about that, they have the right behavior on the empty sequence. Any on an empty sequence is what it should be. That is. So what should be any on an empty sequence? Come on. What should be all on an empty sequence? Yeah! Unfortunately, all the is, this, is, that method of strings don't know that. An empty string, you ask, is it all digits? What's the true answer? Is it all digits? Is it, yes, but its digits says no. Is all there is something method of strings return false for empty strings. I've hated that from the moment it got into the language. I've never stopped hating it because it's mathematically wrong. But I'm told that pragmatics is more important than purity. Fortunately, this was not the case for the design of these methods. The union of a, if you get the mathematical point, it would be belaboring it. If you don't get it, I don't have time to get it across. The built-in dict class, built-in dict type, has a new special method. It doesn't make any difference unless you subclass dict. The under missing under special method is a hook method, meaning a method that is there basically for you to subclass. Unless you do override it in a subclass, forget it's there. It doesn't do anything. It's not meant to be called or anything. When a key is not in the dictionary, 2.4 behavior, just raise key error. 2.5 behavior called missing. What does missing do by default? It raises key error, QED. So unless you override it, you'll never know it's there, because it does just what it used to do. But if you do override it, you can do whatever you want when a key is missing. And a great example is Mac there in collections. It's the default dict. It basically overrides missing to ignore the key and instantiate a default factory. Actually, it checks, because if self-default factory is none, it still raises key error. But you can change or set at any time a default factory that gets called so to generate values for missing entries whenever you ask for them. So for example, consider a bag. A bag maps, say, strings to the number of times you've seen them. Multi-set or bag. What should a missing key be mapped to? Well, 0. Obviously. So use a default factory of int, and you're done. You have a map. You have a bag. Because int, called without arguments, returns 0. Basically, all the built-in types called without arguments return their empty or 0 instance. It works works for all of them. Bool open closes false, dict open closes an empty dict, list open closes an empty list, and so on and so forth. And this nice regularity turns out very nice here, because often what you want to do here is basically to use a built-in type. But you can do more. And you can do your own override of missing for more nefarious purposes. For example, you might have most strings should pass untouched, but a few of them I want to translate. Well, make your own little subtype of dict and basically implement missing self-key as returned key. So in your code, you can just always index this thing, and most of the time you'll just get the string unchanged. Except that if it's actually in the dictionary, then you'll get whatever you put in correspondence to it. It's possibly, although conceptually speaking, RAAI is what moves me most about 2.5, this is the thing I'll end up using most often, because it's a functionality I've needed a lot of time. Okay, then we have C-types. So C-types is available for Python 2.2, I believe, and later, as a third-party module, but it got integrated in 2.5. It's basically a foreign function interface. You can load any existing DLL or SO or SL, depending on your operating system, and call any function it contains as a method. And of course, as the name of the module suggests, you can essentially map Python types to C types and vice versa in order to be able to pass arguments and get results. It's possibly the most dangerous addition to Python ever. Make one mistake, you crash. Bad. Not exceptions about it. You crash. Yes?
What does FFI stand for?
Foreign Function Interface. Anybody who wasn't doing Lisp in the 70s need not worry about it. Nobody uses this term anymore. But those of us who were of this band then are going, yay, finally, we got one. The problem with Lisp is never got a standard one, but that's another debate. Elementary, just as C-types, is something you could download, and you still can. Actually, I believe that in the case of elementary, you get more functionality if you download the non-standard implementation, but it's not much more. And the one that comes with 2.5 does the main thing, supplies you elementary, element path, and element include. It's basically like a DOM, but yes?
So why isn't the most current elementary integrated? It's a subset of what's available now.
What we want to offer there is something very stable. Python gets released every year and a half, 2 years. So if there's some great, absolutely wonderful functionality that will be released every 2 or 3 months, that just doesn't fit into Python. So what we released, I'm summarizing to the bone, is a stable subset. We tried doing it another way many, many years ago with the XML stuff. I don't know if you ever fought with _XML plus. That was such a total nightmare. Trying to have something that was stable, but you could like download a third party which monkey patched himself into your Python install, because the XML people were releasing every day, and we didn't even then want to release a new Python every day. Never again. Been there, done that. I'll leave that to younger languages, most have to. I want Python to be stable. That means it can't have the latest and greatest version of something unless for it's guaranteed to be stable for the next couple of years. So basically, it's like the DOM, except instead of mimicking Java uselessly, it's very Pythonic. So you use stuff like a bit like a list, a bit like a dict. And you also get functionality that's similar to the pool DOM, if you've used that in the existing Python XML, which is basically a reasonable compromise between the fact that a completely incremental event-driven interface for parsing like Sax is kind of challenging to program for, except for very simple things. And the DOM takes just all of your memory if you ever deal with big documents. You basically do it incrementally, but node by node. You still get a little piece of in-memory representation of the DOM or element tree. There's some difference between pull DOM. Like pull DOM by default throw away things, and you have to explicitly ask to, okay, drill down now for this subtree. Element tree by default keeps the subtree, but you can tell it, okay, I don't care about the past stuff anymore. It's not. If you've used pull DOM, it's very easy to move to element tree. Then we have a little bit better support for functional programming with functools. Functools partial is for so-called partial application, which I will keep currying to the end of my days in honor of Haskell curry. But I couldn't prevail in that debate. And there's a couple of more practical things, such as update wrapper and the equivalent integrator wraps, to basically make sure that if you ever wrap a function, and people do that all the time, you wrap it right. Basically, you get all the metadata, such as the docstring and so on from the function you're wrapping. Another very useful practical thing is forget all the old MD5 and SHA module where in the FAQ. So how do I do SHA 512? Answer, you don't, because SHA wasn't maintained. So now hashlib has all of SHA 224, 256, 384, and 512. If you don't care about cryptography, you won't care. But the interesting thing is that it can work on any platform because it's pure Python, but if you do have OpenSSL around, it will automatically use it for the computationally intensive part transparently for you, which is quite nice. I'm sure if you really cared about that, you're probably already using either PyOpenSSL, PyOpenSSL Extended, or PyCrypto, but this is more transparent and more obvious and more simple. Last but not least, actually not quite last, but close,